My name is Ian Ross. I am a data engineer in the Center for High Throughput Computing at UW-Madison. Um, that basically means that I think of myself as a data plumber. So how do I make sure that my data and my job, my computing task, can get to the right machine and can do cool science? That's sort of the central nugget of my identity right now. But I also do a lot of AI adjacent things within the center. So I act sometimes as AI coordinator in terms of, how do we make sure that we're supporting users and making sure that they have access to the computing that they need to do all the cool science that's now possible because AI is everywhere. So this is a little bit kind of follow along-ish. Obviously, you can kind of keep these slides and go through it later at your own pace. But if you'd like to kind of tag along and kind of go through this example as we do, instructions are here. So the link to the slides is at the top, and we encourage you to go ahead and log in to either AP40 or AP41, whichever you have access to, and go ahead and clone the Git repository. So I'll just quickly do that.
And as a quick note, so the example that Ian's going to go through should work fully um, as a set of jobs submitted from AP40, AP41. If you don't already have an OSPool account, um, you'll just be able to watch and not hands-on follow along today. But we encourage you to apply for an account after the training if you're interested, so that we can get you set up with that access so you can do the examples yourself and have access to the OSPool.
Perfect. And so what I just did there is I logged into AP40. I didn't have a public and private key set up, so I had to go through the web identity uh, management system. But now here I am, and I went ahead and cloned the tutorial. I can cd into that directory. I can remember the name, and here we are. Welcome back to this later. So let's get back to some slides and get talking. Okay. So today we're talking about how to run Pytorch in the Open Science Pool. I want to be very clear that this is not a PyTorch tutorial. We're not going to go too deep into how to actually create a model, how to actually use PyTorch. We're just kind of using a very simple example as a um, learning thrust for kind of understanding how this library interacts and can be run in the OSPool. So what is PyTorch? I'm sure some or all of you are already familiar with it, but it's a very, very, very popular tool for creating training and running deep learning models. So it kind of has lots and lots of nice features for training and lots of nice features for running inference. And it's really become sort of the go-to software package for deep learning. And we're going to talk about how to use it today in the OSPool. And the example that we're going to use as our motivation is a little contrived, but it's a fun one. We're gonna train a dog cat classifier. We have a bunch of images that are labeled as either a cat or a dog, and we're going to use that to train a model. Then we're going to turn around. We'll give it a new, fresh set of pictures that have unknown pets in them, and then we will have the model see, is this the very superior dog, or is this the inferior cat? Um, you can see I'm putting my stake in the ground. Dogs are the better pets. And so if you need to leave now because you like cats, go ahead. But no, we love cats too. So that's the task today. We're going to train a model, and we're going to use that model to see which types of pets we have, let's say in our team Slack channel. Now, this is a fairly small example, but you can imagine that other scientific tasks will be much bigger. In this case, this is something we could very easily run on our laptop. But for bigger models or bigger data sets, if we're talking hundreds of thousands of pictures of dogs and cats, then suddenly things won't work as well on our laptop. So, limitations on a laptop. You may not have, a beefy enough GPU to actually hold a model of a relevant size that you need to use. You may run out of memory. You may have a data set that's just too big to fit on your laptop. Maybe training takes 12 hours to run, and you just don't have that much time to sit at your laptop having it active. Maybe you want to go home at the end of the day without having your laptop uh, bound to your desk. Or maybe, and this is a much more realistic case, maybe you want to run a bunch of variants of a model. Maybe you want to do a hyperparameter sweep where you're trying different learning rates, or you're trying different model architectures, or you're kind of trying different data sets or different settings to figure out, what avenue is going to work best for my science. What type of model, what types of parameters will result in a model that has kind of the strongest predictive power. Or, maybe you have some combination of all these things that's kind of limiting what you can get done on your laptop. And so that's where the OSPool can come in and immediately start helping. So the central idea behind the OSPool is simply to use more computers at once. So, great, I can run something on my laptop. What could I do if I had a room full of laptops or a room full of desktop computers running Windows XP, apparently, not Windows 7. So that's the idea here. So we have tens of thousands of computers waiting out there to do computing work. And we just need to figure out how to get your job, your task out to some of those machines, so that those machines that are sitting idle can start doing work for you, getting cool science done. And we're not running Windows 7 in a kind of a lab classroom settings. Our machines look more like stacks of racks full of servers and data centers all over the country. What does interaction with the OSPool actually look like? So you, as a user, will interact with the OSPool by connecting from your computer into what we call an access point, an AP. So these are, AP40 or AP41. So you'll SSH to that machine. On that machine, there's kind of a few different areas that you can store data, store software, store scripts. We'll talk in a lot more detail about those. But then from that access point, what you do is you define the shape of your work. What are the resources that you need? What are the input files? What are the scripts? What are the environment setup? All these things that really define the computing task that you need to get done. You take those descriptions, you write it down in a very specific language that our software called HTCondor understands, and Condor will take that description, look at all the resources that it has available across the country, and start doing that matchmaking process and say, okay, well, this job over here needs 16 gigabytes of memory and 2 GPUs, and this machine over at FIU is idle and it has 2 GPUs and 16 gigabytes of memory. Let me move that job over to that machine, move the data inputs, move the scripts, and start it. So HTCondor is kind of the central manager that takes requests from users, takes idle resources, pairs them up, transfers everything required, and starts the process. So terminology, access point is where you, the user, will log in and kind of submit work. And then where that work happens is what we call an execution point, an EP. These EPs exist all over the country. So every green star on this map in the lower right-hand corner here is a site that contributes resources to the OSPool. I don't remember exact numbers. Looks like 40-ish. But yeah, geographically distributed across the entire country. And we want this to be kind of as easy for you as a user as possible in order to get jobs running everywhere. So by attaching a bunch of different compute clusters across the entire country, you just get more access to more power. So we call this entire process high throughput computing. A lot of you may be familiar with high performance computing, but high throughput is thinking more in terms of, okay, we have a large number of smaller machines, and we're interested in how many hundreds or thousands or hundreds of thousands of jobs we can get through over a long period of time. So high throughput computing. What are the advantages of a system like the OSPool? Well, it's available at no cost to you. That's pretty fantastic. A lot of users have access to these machines, and a lot of these resources may otherwise be sitting idle. So a lot of campuses are happy that the resources are getting used, and users are happy because they get access to free resources. And then another big advantage that you have over running something on a lab machine or your laptop is that Once you describe that work to HTCondor and hand it off to have it kind of manage it for you, you could just walk away, and Condor will find a machine somewhere and run it for you, and we'll move results back to the AP. And it doesn't matter if you're sitting at your laptop that whole time. So you could just submit thousands of jobs, hand it to HTCondor, go about your business, go enjoy the beautiful sunny weather that we have in Madison today, and or continue doing lab work or whatever else you may have to do. So it's the big benefit of being able to define huge volumes of work, hand it off to a system, and then just have the system manage it for you. Now there are some maybe not disadvantages, but some um, upfront payments that you have to make. So there is a learning curve. Um, it is a unique language, a unique description of your work that you have to pass to HTCondor in order to make it run effectively. Um, and then the other big conceptual hurdle for some users is that it's a non-interactive environment. So these jobs are running somewhere all over the country. You don't know where, and you're not going to be able to interact with them directly. It's a batch framework where you kind of hand the work off, and then you kind of get the results at the end of the runtime. You're not able to directly interact and kind of fix things, and there's no GUIs to click, and no live at the keyboard action for the running tasks. And so that means it's can be a little hard to do initial testing, and we'll kind of talk through how we make that process easier. But it's not really meant for interactivity and very short iterative development cycles. So when I think about starting to define and run a workflow within the OSPool, I kind of think conceptually about three different steps that need to happen in order to get things working smoothly. So, first, I'm going to be developing and testing things locally, on my laptop or on a lab machine. And then I'm going to be doing the work to actually get it running on the HTC system, get it running in the OSPool. And once I have science flowing through the OSPool, then I'm going to kind of revisit, take a fresh look at it and say, okay, what can I do now to make things better? What can I do to get more from the OSPool? So we're going to start by talking about that first step, development and testing. And so the goal here is just to create, kind of the smallest piece of workflow that you can locally, and then kind of grow it so that it can run and work out on the OSPool. So this kind of you can think of it as writing and running scripts locally and setting them up so that they can run at scale in the OSPool. So making sure that your Python script runs without errors, making sure that it can read in data and do some amount of work and spit out the expected output, or making sure that the pipes that I as a data plumber like to set up are actually functioning. That stuff is flowing through the application and doing what you expect. And as you go through this process, you'll be working with a subset of kind of your live data just to kind of A, get a sense of whether things are working, and B, get a sense of order of magnitude, what are the resource needs that I have here. So if my training data set is 100,000 images, maybe I'm working with 100 on my laptop. How long does it take for that process to run on that small subset of data? How much space is it taking up? How much memory is it consuming? And if I'm thinking about GPUs, it's a little bit hard to map laptop to OSPool, especially if you have a MacBook. But kind of getting a sense of do I need something big and state of the art, or am I happy with something that's a little bit older, a little bit smaller, and a little bit more readily available in the OSPool? And then the third thing that you're thinking about at this stage is, okay, great, it runs on my laptop. We saw on that map that there's 40 different sites scattered across the country, different administration teams at each. It's a different version of Linux running at each site. How do we make sure that the software that runs on my laptop right here can go to one of these other sites and be successful? Because we have to worry about moving all of the software, all of the environment with your job in order to get it to work. And so the process we use for this is something called containerization, which we'll talk about in more detail. So this is the three key things that we want to accomplish during our initial development and testing phase. So I'm going to hop over back to AP40 and kind of just show this very simple training script and what it looks like. So here we go. Okay, so I am in kind of the main directory after I cloned the repository. And within the train directory, you can see if I ls, there are a few different scripts, but what we're interested in looking at is the Python script itself, the Pytorch script here. So the slide kind of outlined the three main pieces of code that happen within this training script. So the first is defining the model itself. That's what this class cat and dog convnet is. That is the convolutional neural network architecture that we're defining. Again, not going to go into any of the details here other than showing it very briefly and saying this is what we do to set up a model. We also define a data set handling class. And so what this will do is, we'll point it at our pile of data, and it knows how to read, in this case, images off the disk, transform them in the necessary way to put them through the model. And then because we're doing a training labeled data, it also has a little bit of information about how to actually read and understand those labels. So that's important in the training process. So basically what happens is, we're reading pictures off disk, and we say that if and the name of the file includes cat, then it's a picture of a cat. And we've just kind of set up a convention so that a label of 0 on an input is a cat and a label of 1 is a dog. Then finally, we have the main part of the script, which defines an interface so that we can pass in different options at the command line. When we start running, it defines how to go through the data set directories, prints out a little bit of information as it goes, and it actually drives the training process itself. So it will create the model, move it to the GPU, read the inputs, convert them to a tensor, put those through the GPU, and do all the deep learning magic that I will just call it magic in the interest of this tutorial. So that's all that the script takes. It's, how do we get data in? What do we do with that data? And how do we kind of define the process and the inputs and the outputs of that interaction? Cool. Now, I think back over here. So I'm not actually going to run it on the AP, but conceptually what's happening here is we have this script, this training script, and when we are running it and writing it on our laptop, what we want to do again is we'll have our data sorted in a data directory. We want to push that into the training script, which again does the deep learning magic, and out pops a model, which we just write to a directory, the current working directory, and we save it as model.pth. So, as I'm going through this, okay, I'm thinking about what am I doing? How am I interacting with my data? How do I want to define, the different options that might exist within the training script? So, in this case, we got our data, our training data as a zip file. So as I run the script, okay, what are the two things that need to happen? Okay, first I need to unzip the training data set. So, step one, when I am going to be running this in the OSPool, I can imagine that I'm dropping this zip file in my working directory on the EP, on the execution point. The first thing that needs to happen is the same thing that needs to happen on my laptop. I need to unzip that training data. So the first thing that's going to happen is I just write all that data, unpacked into a data directory. And then I'm going to do the training process. And that's just going to be invoking Python, passing in that data directory, and then defining a few other options. So these are just things that I kind of built into that script. So where am I going to save the output, and how many epochs of training am I actually going to do during this process? And again, so when you're doing it locally on your machine, you know, you should be thinking through these things as if you'll be running it on the OSPool because you will. You'll be doing more of a minimum viable product type mindset. So just doing a subset of the data and making sure that the pipes work. Okay, so that was a big conceptual leap. Let's do a quick pause here and we can answer questions that you might have about your workflow. Wait, Christina, why am I an outlier on the team?
I would say the proportion of cat to dog pictures is higher than lower.
That's true. Yep.
John, go ahead.
So, yeah, so are we asking about like how we, so for running a machine learning pipeline, how do we need to set up a workflow for OSG, like distributing the jobs to different places? So, yeah, so my question will be like, how the data will be separated, like go to different machine, do all the data will go to all the machine where you submit the jobs in the workflow? I am a little bit confused about that.
Yep. So, this is just that kind of first step of developing things locally on the laptop. We'll go through how do we actually run these out on the OSPool, including a discussion about how we handle data. And basically the answer is, Condor will move it for you, either using kind of a direct file transfer or through something called the OSDF, the Open Science Data Federation.
Yeah, and when we get to that example, I think it'll be clear. We have a training example, and then we also have an inference example. And the training example is going to run one time and use the full data set. And if you ran it multiple times, you would need the full data set for each run. Whereas the inference you're going to see can be split into independent runs. So if you have a whole data set you want to inference, you can send off little chunks. So that should appear in the upcoming.
Yeah. So David, you asked about does this work benefit from GPUs? Is there something in the code indicating that? And so in deep learning processes, yes, training speed and inference speeds are greatly improved if you use GPUs. You usually can run it on CPUs, depending on how much physical memory you have on the host. But it's depending on the task, it can be 30 to 100 times faster on a GPU. And so this is the magical line here that does, basically this is telling Pytorch, I want to use this device on the machine. If CUDA is installed and available, that's kind of the interface to a GPU. Use that. Then this else MPS if Torch backends MPS is available. So this is something I include when I'm doing work on my MacBook Pro. This is the metal performance shader. So MacBooks don't have NVIDIA GPUs, so you can't have CUDA, but they have a lot of powerful GPUs in them. This is how you use that for Pytorch on a MacBook Pro. And then else CPU. So if no GPU is available, yes, we can just run it on the CPU.
I have one question. So the container is also part of the workflow, or it's something different?
Yep, we're going to talk about containers, I think, next. Yeah. Let's just do it then. So great, we have something, this stage that works on our laptop at a small scale. But like I said, we need to make sure that this will run kind of anywhere within the OSPool. And so that's why we need to go through an additional hoop of creating either a Docker or an Apptainer container image. So what is a container? So these are basically ways of packaging up software so that they can be moved and run on almost any machine. Back when I first got started 5-10 years ago, it was a huge pain trying to distribute software across the OSPool because we had to make sure that all of your basically we would make a big giant tarball of all the Python dependencies that we had, move it, and kind of hope that things lined up and system libraries were compatible and all that. But with Apptainer and Docker, what you do is you kind of define a container. You kind of move all of your software into that container and you save it and you tell Condor, when I run this job, pull down this container, which contains all my software and all my environment, and run it within that little tiny ecosystem. So the benefit is, you have to build it once and you kind of have to learn how to build it, but you can use it pretty much anywhere after that point and kind of makes things nice and reproducible kind of as a side effect of defining and creating the container. So the container, it is a read-only sort of. I kind of think of it as a mini virtual machine, but it's read-only, and it should really only carry kind of the smallest footprint of things that you need within the job. You don't want to kind of stuff it with a bunch of unnecessary objects and software and just kind of make it unnecessarily bloated and large. And also, it should only be the things that aren't changing often. So when you think of running a computing task, your data and oftentimes your Python code itself, those might be changing often, and you don't want to have to create a new container every time that you add a small line to your Python script or every time you add 50 new images to your training set, right? So usually you don't want to bake those things into the container image. You want to kind of keep them on the side and move them using other Condor mechanisms. So what do you put in the container image? Software, libraries, dependencies, kind of environmental setup, environmental variables. So we like to think of an analogy we like to use is if you're going camping, you have a backpack. Usually that backpack has your essentials. It has water, it has a tent, it has a sleeping bag, it has things that you'll need every time you go on an overnight camping trip. But the actual destination of your camping trip dictates a lot of other things as well. So maybe you'll need sunscreen, maybe you'll need flip-flops for the beach, you'll need different food every time. It will be easier to kind of swap those in to an existing backpack if the backpack has all the essentials already bundled up and ready for you. So there's a number of different container softwares. The two main ones these days are called Apptainer, which used to be called Singularity, and Docker. And so within the OSPool, Apptainer is the preferred approach. You can build your Apptainer images directly within the OSPool. And then the output is called a Singularity image file, SIF, a SIF file. And those just kind of live on disk and they get moved along with your job to the EP. And your job starts running within those. Docker, you can build on your computer and you upload your container image to Docker Hub, which is a public repository. Then the OSPool, if you are using a Docker image, it will actually convert to an Apptainer image on the fly. But in the OSPool, it's easier to just use an Apptainer image from the start. And they have, as you can see here, different kind of syntax for how to define what these container images are built from. So on the left is a Singularity or an Apptainer image definition, and on the right is the roughly the equivalent Docker file, Docker definition. And so these are available in the GitHub repository underneath separate containers. Come up here. Inside the container directory, there are different ways of building the image and using Apptainer. So two different Apptainer options and then a Docker file option. And the two Apptainer, let's just talk through them. So when you build a container image, what you do is start from an existing image and then you kind of add your pieces on top of it. And so we always recommend starting from a base image that kind of has as much of the complicated stuff pre-installed as possible. And so Usually in the Pytorch world, this is either starting from something that has CUDA installed already, or starting with something that provides a strong Conda environment already. So the Aptainer example on the left here starts from a sort of blessed Conda Forge image, and it builds on top of that, installs the additional pieces of software that we need in our container. In this case, it's adding Git, Vim, curl, wget, zip, and then installing Pytorch, a bunch of other Pytorch things. And then the important piece here is the CUDA libraries themselves. So that's one approach. Start with Conda and then use Conda to install the CUDA libraries. Another approach is the Dockerfile example here, where you start from an image that has those CUDA libraries installed already, and then you build on top of that. Not a huge difference in terms of, they both work perfectly fine. It's more of a which dragon do you want to slay in terms of installing CUDA or installing kind of the rest of the library requirements. Okay. And so now we've done all 3 steps of our kind of local development process. We've decided how we're going to interact with it on the command line. It's this 2-step process where we unzip and then we run the Python script. But now we have to go through the process of converting this workflow that works well on our laptop into a job that we can submit into the OSPool. So how do we distribute this work on an HTC system? I guess before we go into that, I'll do another pause for questions.
So, sorry, I'm asking again a question. How the Conda environment, creating a Conda environment is different from having this container? Like it's like just a virtual machine with a Conda environment. It's like that, or is there anything else that is different in this? I am confused about it because we are doing most of the steps are like the Conda environment, no?
Yes, that's true. But you also can have additional. So this is kind of the smallest possible example. This is essentially running everything in a Conda environment. If there are other external dependencies that aren't capturable in Conda, then you can build them in. So in this case, these are additional software features that we want in our container image. Can you see my mouse okay.
Yes.
Okay. So in this case, we have decided that Git in a few text editors and a few ways of grabbing files. And, this is the really important one is we have to install zip because we know that we have to take a zipped up, a compressed image, a compressed file, and uncompress it. And so we need zip around to actually do that decompression and do that unpacking. So yeah, in this case, Conda gets us most of the way there. But in this case, we don't know for sure that zip will be installed on the machines where we're landing. And so we want to make sure that we bring it along with us. So any tool, that you might need within the flow of your work, you want to make sure that it's included in your image container. Good question. And don't feel bad about asking questions. That's what you should be doing. Okay. So now we want to figure out how we define our job to an HTCondor system, a high throughput computing system. So there are a number of different components of the job that we need to make this Condor software aware of in order for our work to be successful. And so we kind of break it into these 5 different categories. So, there's the environment itself, which we kind of handled with a container, right? So what is the software? What are the libraries? What are the other dependencies that we have within our computing environment? There's the executable and arguments. What is the actual command that gets run? What is the interface? Like, what are the parameters that we pass to that executable? There's the input files and output files. What are our data needs? What is this computation doing? What are we hoping to spit out at the end of the work that we're doing? There's the standard out and the standard error. So this, if you're running a script on your laptop, these are the messages that are getting printed to your screen as you go. So where do we actually want to save those? Because those can be very, very useful in monitoring and keeping an eye on your job. And then there are the actual resource requirements. So how many CPUs, how much memory, how much disk, and what is our actual GPU requirement for the task? So now we're going to talk through each of these and define how we describe them to HTCondor in order to create this description of our work to hand off to the scheduler. So we already did the software environment piece. So let's start converting the executable and the arguments section into something that Condor can run. So as we're going through that development process, we recognize that we had a two-step requirements, two steps: unzip the data, then run the training script. And again, because we can't interact with a running job directly in an HTC system, what we're going to do instead is create a little bash script that will kind of run those commands for us. So this goes by a few different names, either an executable script or a wrapper script. So this is something that we hand to Condor and we say, this is what's really going to define the work for our computing task. And then the next step is doing the rest of it. So this is, and I want to jump, no. Yeah, I think I will jump back to the terminal and we'll actually look at the submit file now. Okay, so this is a submit description file for an HTCondor job. And so it handles all the things that all of those 5 boxes get checked here. And we'll just kind of talk through each of these sections. So the first one we're kind of categorizing as job execution and data handling steps. The first one here is saying, I have created an Apptainer image. It is stored at this address. We will talk more about what this OSDF thing is in a little bit. But this is telling Condor, this is my container image. This is what you should use when you're launching the job. The shell command is, what is that wrapper script that needs to get started when the job begins on the execution point. The transfer input files is the additional files that aren't within our container image that we need to bring along to actually do the work. That's, again, our wrapper script, the actual training script, and then, again, we're storing the data in something called the OSDF. Ooh, what a mystery. And then finally, what is the expected output? So Condor, by default, will just write anything that's sort of new in the sandbox directory back to the AP when the job completes. But most of the time, you want to kind of select your outputs that get moved back. And so in this case, the only thing we care about is the model that gets spit out at the end. So then these 3 lines here are kind of defining what we want to capture and where we want to store sort of different logging information. So output and error are, again, those standard out and standard error. Those are the things that my script and my Python script are kind of writing to the terminal. And then log is the Condor log itself. So this contains a lot of information about the job in terms of what is its current state? Has it started? Is it executing? When it's completed, what were the actual resources that it used? And then this section here is a very straightforward one where we just define the computing resource that we need in terms of CPUs, memory, disk, and GPUs. So we have used our kind of back of the envelope calculations from our initial kind of laptop exploration. We know that a single CPU, a single GPU, very modest memory, and a small amount of disk. And so it's important to remember that because we're using an Apptainer image, we have to include the size of that image in our disk request because Condor moves that to the execution point and starts it there. And finally, there are ways of defining what GPUs you can match to within an HTCondor pool. So this boils down to how new we want the GPU to be. That's what this capability is. It's essentially as NVIDIA releases a new GPU, the different families of architectures have different, they call it CUDA capabilities. So this is saying, everything's 7.5 and up, which I think, I don't remember offhand. It might be everything that's like a 2080 and newer, I think might be included in this bucket. And then we're saying that we only need 4 GB of VRAM on the GPU itself, which is a very small, modest amount. And then the final line here is just telling Condor that we are queuing a job. And we will revisit that later when we start to do more work. And I've talked through all these, but this is good. I'll talk through that again. Cool.
What's your question, John?
Yeah, so for example, for machine learning, sometime or even other workflow, we have a very large data set. Even the zip file is bigger and the CIF image is also very bigger. So then how do I know that I will have resources that will, like, if I put my, like, is there a limit that I have to put on this memory allocation? Is there some limit that we have to know, or?
So there's no limits. What you can do, there is a command that I'm showing here called Condor status. If you do -GPUs, it kind of restricts it to just machines with GPUs. And it shows kind of a live snapshot of what is available within the pool right now. You can see that it lists a few things about the types of GPUs here. But what you can do, I don't know. You can,
Just to
is there a
clarify,
recommendation?
you said memory, but you talked about data set size, and data set size can also sometimes mean disk. So were you talking about GPU memory, CPU memory, RAM, or scratch space on the local node for your data set, or all three?
Well, this is what, because in the file we are specifying these, right, numbers. And that is where, like, sometime, like, just because I am also new in this, sometime the people in the LIGO collaboration, they submit their jobs and they have some problem because their job fails. And I think the reason is this. So is there, like, as you mentioned, we can check what resources are available, but I think these numbers are important to know, right? And sometimes the CIF images can also be very big.
Yeah.
So I just wanted to ask if there is a way we know that we should not go extend beyond some particular number or
You can
something. Or
request as much as you want. The job might not start.
okay, yeah, that's something. Okay.
Yeah,
Yeah.
but I think it's always worth trying. Like it's always worth requesting. You can usually estimate how much disk space you need because you know how big the container is, you know how big the data set is, you probably have some sense of how big the output data is. Um, Estimating memory, like how much you need either RAM or GPUs, is a little harder, but it's also okay to try something. And if your job gets killed or put on hold, or there's an error message about being out of memory, to just try again with a higher value and see how it
Yeah.
goes. So there's a little
Yep.
bit
So
of like empirical trial and error in this process.
yeah. And one of the things I'll talk about at the very end is that, so two things. So Condor, if you request 4 GB of memory, say, and you end up using more than that, Condor will put your job on hold and say, hey, you only requested 4 GB and you used way more. Please adjust your requirements because you know, if everyone requests kind of over request memory, then bad things happen. And so Condor will kind of put your job on hold and indicate that you have kind of overconsumed what you requested. But the flip side is when a job finishes running, Condor will, in the log, spit out information about what resources you actually used. So you can use that as a tool to kind of say, oh, okay, well, I requested 4 GB of memory. I only used 2. So maybe if I dial that knob down, I'll have access to more machines because the lower your resources, generally the more machines you have access to. maybe I'll be able to match more and get more throughput. So, kind of use, your best guess to get started, and then you kind of dial in those requests as you kind of interact with the system and find success or failures.
Thanks.
Okay. One of the things I sneakily did to get the ball rolling here. So now we have our submit file, and the way to actually give it to the HTCondor system is to just type condor submit and then the name of the submit file. And so then I'll just do another one just for fun. It says it's submitting a job. It's submitted to this cluster. And then if I do a condor queue, you can see I have a lot of other things going on, but these bottom two are the ones that I've submitted in the last few minutes here. And so you can see there's this nice output kind of indicates the state. For this batch of jobs that I've submitted 5 minutes ago, it's already running. The one I just submitted is not yet running. And then there's another tool called Condor Watch Queue-F. Condor Watch Queue. So this will kind of continuously poll to actually keep track of the state, because we don't want users typing Condor queue, Condor queue, Condor queue every second for as long as the job lives. We wrote another tool that will basically tail the log file and gives you information about how it's going. So right now you can see that job with this long ID is currently in the input state. So that means that it's currently transferring my input files, which are my singularity, my obtainer image, and my data set over to the execution point for running. And so we'll kind of let that spin in the background a little bit. We will keep on moving. Okay, any other questions about submitting jobs? Okay. Now we can do our data talk. So we saw that in this transfer input files line, we kind of had two different sort of signatures for what the files we're moving. We have the train.sh and the train.py, which are files that are living kind of alongside that submit file on the AP. And then we have this third one, which is OSDF:///OSG public data tutorial, blah, 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 blah. Okay, so what do these things actually mean? So when you log into one of the access points, you kind of have two different spaces for storing data. We have the what you are plopped down in when you first log in is your home directory, but you also have space in /OSPool. And so these are kind of the paths that are attached to the access point for you interacting with. And then we also have external data spaces. So these are, in this case, these files are stored in a public space called OSG public. And then we also have something, a conceptual space called my origin. Oh, and we'll talk about what that means. So what lives in home? So this is the file system that you're interacting with for the most part on the AP. You should always be kind of preparing and submitting jobs from your home directory. Things that you move out of this home directory should be your small files, things that are less than, say, a gigabyte. These are your Python scripts, your wrapper scripts, very small parameter files, very small data sets. By default, you have a quota of 50 gigabytes. And this is kind of the very familiar, you just define the name of the file in your transfer input files, and Condor will move that over. So many small files should be living in the home directory. So the OSPool directory is what we call the staging space. So this is a file system that's used for much larger files. So this is where your obtainer image goes. This is where big data sets will go. It is very bad at small files. So do not store large numbers of small files here. It's for a small number of large files, not a large number of small files. So and the reason is it is a different type of file system. And small reads and small writes into that type of file system create a lot of overhead and can really, really slow down performance for everyone. So it's really important so that you're just moving, one or two or three, the smallest number possible of the biggest files that your job needs should be living in the OSPool staging area. And so this is where that OSDF colon slash 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 oh geez. What's it called? Protocol? Yeah, protocol. So that's what that means. So the OSDF is, like I said, the Open Science Data Federation. These files are basically getting served up through another software suite that we developed called Pelican. And OSDF is an instance of Pelican, and it's basically a way of caching and moving your big data files throughout the entire OSPool ecosystem, the nationwide cluster of clusters, so that the data should always be living nearby to the compute where your jobs will land. So think of it as a nice way of distributing your data, your big data across the country. It creates a lot of uh, reduces a lot of the transfer overhead because it's kind of caching as it goes, and it's a lot more effective for getting these big files to your job. And then it has other nice features. For example, if your inputs are hard up, you can kind of unpack it on the fly using things using this question mark pack equals auto. So that will say, all right, Condor, when you're moving this file over, unpack it as you go. This is a tarball that I want kind of unwrapped and unpacked at the execution point. So as you're going, just write it out to disk. And then there are additional origins, additional data spaces that exist, some of them public where data may be living. So again, this is served up via the Pelican interface. Kristen, do you want to say anything about the Pelican versus OSDF?
No.
Okay.
The OSDF is like kind of like a special version of a Pelican data federation because the Pelican kind of grew out of the OSDF. So it has some special features like the canonical way to describe the location of a data file in the data federation is with this Pelican URL. But because the OSDF is special, there's like a shortcut URL you can use. Just little things like that.
Okay. So yeah, here's a nice summary. Things that live in home are your small things. Things that live in OSPool or these external data spaces are the large ones. You can move things back into the OSDF at the end of your job as well. We'll talk about that later. But yeah, small things going home, big things and slash OSPool. It's kind of the easiest rule of thumb. And then another situation that comes up pretty often is, we talked about trying our best to avoid large numbers of small objects. So one recommendation we make is that if you bundle all of those small things up into one big file and then move that back, typically is a much smaller overhead for the system as a whole. So this is just a little bit of information about how to do that bundling and do that extraction at the AP. Okay, so we can pause there. Questions about data? Oh, I see David unmuted, so
Yeah, I
I
have
sense
a
one
question,
coming.
Ian. I just happened to have been transferring data for a sort of project over there. And what I was wondering about was setting the permissions on the files. Am I doing anything useful at all by, say, turning off a read for other on those? Is it keeping an average user from looking at my things on OSDF, or should I just assume that anything's readable? I understand when it gets to an execute point that, who can look in the core memory can see my stuff, but is there a useful way to say how we should be using the group and the other permissions when we drop things on OSDF?
Yeah, Christina, do you know
Um,
best recommendation?
yeah. So the to access files using the Pelican tooling and the Pelican URL, I think you have very little control in some sense. We are the ones who are making sure that any data that you've staged in a folder that is accessible via an OSDF URL is only accessible by you, say, or your group, if it's a group folder. So the default for AP 40 and 41 is that you have a like OSPool data folder, and only you should get the right token essentially to read or write data to that location. Separately, the backing storage is also accessible to you. Like you can interact with the file system directly, and there you should just use best practices for a Unix file system. So don't make your files world readable. How those things interact, I'm actually not 100% sure. Like if you took away the read bits of a file in the file system and then Pelican tried to access it, I don't know the answer to that question, but I could find out.
Okay,
So,
thanks.
so yeah, can you shoot yourself in the foot? Not sure.
Okay, I just noticed in the past year everything was readable by other, and I was just changing it. I understand, of course, on AP 40 it might affect it more, but maybe not in the execution only. Thanks, guys.
Cool. Okay. Checking back in on our job. So when we last left it, it was in the input state. Now it's in the running state. So it has finished transferring the input files and it's actually doing the training now. And oh, you can see that second job I submitted is also now running as well. It would finish by now, but that's okay. So what I will do is just kind of show. This is that HTCondor log. It's not a very good view. This is what that HTCondor log looks like. So it kind of prints out everything that HTCondor knows about your job. So you can see that I submitted it at 2:15. Then it started moving the inputs. It finished that step 10 minutes later. It said, okay, now I'm going to start. I'm going to use this singularity image cat dog conda.sif, and then it started executing. And you can see every now and then it will spit back a little bit more information about how much memory it's using and how much disk it's using. And then, like I said, once this job completes, it will write a summary of that information. So hopefully in 5 or 10 minutes, that will be there and ready for us. Stop that. Okay. Okay, so now we've done the work of submitting our first training task into the OSPool. Now we want to think about, okay, how do we actually improve things? How do we make things better? We submitted one job, but I've been talking about hundreds or thousands or tens of thousands of jobs. So how do we actually start to kind of grow things out to actually use the scale and power available to us? So we're going to shift gears a little bit. We're going to pretend that we have completed that model and now we want to actually use it to make predictions of these adorable animals. So we want to run inference on the model that we trained. So let's kind of think about what that process looks like. Again, we're going to start with local development. We're going to think through, okay, my Python script will look pretty similar, but instead of doing training, it's going to be doing inference. My interaction with the data sets will look very similar. These are going to be unlabeled though, so I don't have to worry about that whole label processing piece. And then, instead of spitting out a model, I'm going to be spitting out a CSV file that kind of maps the images to sort of a probability of dogness. So that's kind of my input, script, output, conceptual pipeline in this case for the inference task. But a lot of it is going to look very similar. We want the same sort of interfaces. We want to be able to point the Python script at a certain directory, at a certain model. And we're going to, again, have all of our data zipped up. So we're going to have to worry about unzipping it when it gets to the EP as well. But now, instead of just, one training data set, let's say I'm sourcing images of dogs and cats from all over the place, from our Slack channel, from Wikipedia, from myfavoritedogs.com, myfavoritecats.com. Let's just say we have a ton of different data sets. what if instead of submitting one job, we want to submit dozens or hundreds of these jobs, each one with a different data set? So now we're going to update our wrapper script to actually handle a variable input name. So that's what this $1 is basically a syntax for a bash script, reading the first argument that's passed to the script. And so we're saying, okay, when we run the script, we're going to say infer.sh, and then we're going to pass a name of a zip file. And we're going to assign that name of a zip file to this variable zip. And then within our wrapper script, we're going to unzip that file. We're going to do a little cleanup, and then we're going to run our inference. And so we're using arguments to kind of pass in the name of the zipped data file. So now we have to figure out how we pass that zip file name through our HTCondor job file, job submission file. So that's what this looks like here. So again, our shell is saying we're going to be running our wrapper script infer.sh. And now that infer.sh is expecting us to pass in the name of a zip file. And so when we do $zip file, we're telling Condor, this is a variable. This is a custom defined variable that we're going to be defining from this final statement, this Q zip file from datalist.txt. So this line says, I will be creating a file called datalist.txt that contains a list, one per line, of a bunch of variables. And for each line, I want to use that line as my zip file argument. Right? So datalist.txt looks something like this. When we say Q zip file from datalist.txt, each line gets read in, first it does images 01.zip and assigns that to zip file, then it does the Q. Then it does the same thing for every line of that file. It's just a for loop. So everywhere that $zip file appears, we'll be substituting in a name of a file that gets defined within datalist.txt. And this is a way of creating 10 jobs from one single submit file over a wide variety of inputs. The other thing that we've changed a little bit here as a learning exercise. So you can see that these paths to model.pth and the train.py are now relative paths. So we will be sitting in this infer directory. And now, we still want to pass the model file from our training, and we want to pass the train.py script, but that doesn't live here. That lives up a directory and over a directory. So if we do ls./train, that's where those live. And so when we put this /train model path, that's just saying, I want to transfer these files. They live up a directory, over a directory, and then that's where they live. So you can use relative or absolute paths within your transfer input files. And then the final piece that we're introducing here is something called transfer output remaps. So you could see, let me go back a little bit. When we kind of wrote our infer script, every time we run infer.py, it just spits out a file called dogprobs.csv. But now, if we're thinking about running this in the OSPool, well, every job is going to create a dogprobs.csv. It's going to transfer that back to the AP, and we're just going to keep overriding this file because everything is getting written back to our same directory on the AP. And so we ran 10 jobs, but we moved 10 files back, but we just kept overriding it. So we need to be a little bit more careful, a little bit more thorough in what we do in terms of moving our data sets back. We could build that logic into the wrapper script and rename things there, or we can use transfer output remaps. And so what that says is that we're going to move dogprobs.csv back from every job. But when we do that, we're going to move it to a directory called output, and we're going to rename it to dogprobs, and then we're going to put in that variable. We're going to put in zip file again. So every probability CSV that gets written back will get stamped with the name of the zip file that it came from. Okay, so now let's come back over here and see. Perfect. Okay. So now I'm back in the training directory, and you can see that I now have a model.pth. So my first training job finished. I don't need that second one because it's an identical copy. So I'll do a condor rm and then the ID of the job to remove that job from the queue, because why do the work when I don't need it? Now I'll go back over to the infer, and I'll do a condor submit infer.sub. You can see that it submitted 10 jobs to a single cluster, and those 10 jobs were defined by the data list. It's the substitutions of these zip files in as that zip file variable. So now we can do condor watch queue and alt 10 are idle. So we'll go, look at that. Now 8 are getting moved to 9 are getting moved to the execution points. That should be wrapped up pretty soon. So this is a quick and easy way of kind of scaling up how many jobs we're running. Yeah, John.
Yeah, so I think I missed the first thing when we were this is a tutorial about PyTorch about machine learning. So
Mhm.
whenever we do training, it is recommended we submit just one job. We don't because
No,
my understanding is
no.
when you submit the job, it transfer to different places. So that is where I was confused in the first point. I understand in inference because we already have a model and then the jobs can go anywhere and with the model they can infer. But then the first, is it we always have to do one job for when we train the model or for
No,
PyTorch?
so yeah, good question. So the answer is no. We basically, when you're training a model, to train a model, you're doing a lot of epochs of training. And an epoch of training is taking your training data set and pushing all of it through of your model architecture, doing, all the fancy deep learning magic that I talked about. And then, you do that process again and again and again. You repeat however many epochs you need until you kind of reach some kind of convergence and you're kind of happy with your model, right? So a typical training process is kind of pushing all your data through some number of times. But if we think of, if we want a single model, yeah, we would just run one single job. But what we want you to be thinking about is, um, this was one model architecture with one set of parameters, one learning rate. So one of the things that I'll touch on in a couple minutes is the same way that we kind of defined a variable that changed what our inputs were for the inference. We could define a variable that changes our learning rates or our different hyperparameters. Then we could submit a sweep of the hyperparameters and submit 100 training jobs and have them run, and then we can say, okay, which of these models is looking most promising, and then kind of filter down and say, okay, I had 100 and I was exploring the space, but these 10 over here are looking most promising, and so we can kind of scan the area, kind of find model variants that are looking best, and kind of push those along and kind of let the other experiments kind of stop. So in our example, yes, we only ran one training job, but there's no reason to only do one training job. That was just kind of here's getting started running one. So
But for one model, so to get the one model, we need
yep,
to have one job, right? That's what we will
yep,
train different models and then we want to find out which is the best one. But for one model, we need to submit one job, right? That's what I'm
yep,
asking, because then I'm not understanding how the data will go to different machines and then get back. So
yep.
I
Yeah.
So yes, the
yeah.
one training is one job. Yeah. Um, but yeah, so it's if you submit one job, you'll go to one EP and train there and then come back, right? So it's when you start running multiple jobs that you're kind of getting resources sort of all over the place.
Yeah, and there's a question in the chat about is it possible to specify multiple GPUs to enable distributed training? And the answer is yes. You can just change that number that says request GPUs from 1 to 2 or 4. The limitation will be, are there any resources in the OS pool that like where you can use multiple at once? And to be totally clear, Ian kind of just mentioned this, the GPUs are always all that you use for a single job are always going to be on the same server. Because the OS pool is this distributed network of computers, we can't guarantee that like this server with 2 GPUs and this server with 2 GPUs can actually talk to each other because they could be in completely different places. So you can specify 2 or 4, and that job would use 2 or 4 GPUs on one node. But you can't distribute across like multiple computers working together. That would be more of a high performance kind of an implementation.
Cool. Okay. So let's hop back to the terminal. All right, so 5 of them have finished and 5 are moving. Perfect. So now I'm still in the kind of inference directory. I'll do an ls. You can see that there is now an output directory. Let's take a look. And here are those 5 CSV files that contain the probabilities. You can see that, it doesn't do them in order. It just kind of submitted them all into the queue, and, whatever order they ran, they ran. And so, number 3, 5, 6, 7, and 8 all finished. And they look like, yeah, those look like CSV files, all right. Looks like we have a mix of dog and cats based on the probabilities. Yeah, so that's kind of what the output is when we did that output, transfer output remaps. Beautiful. We'll let the other 5 run. We'll wrap up here. So we're kind of in that, how do we do things better? How do we improve things kind of mindset at that kind of 3rd step in our running things in the OSPool step, or running things in the OSPool sort of work plan. So other things you can do to kind of make things better. I hinted at this earlier. So the Condor log, I printed one here. You should really be dialing in your resource requests, right? So we made a back of the envelope calculation early on in terms of how much space we'll need. But Condor very conveniently tells us exactly what we used during the process. So you can see, per disk, don't know why it reports in kilobytes. I wish it would be a little more readable, but we requested 15 and we used 10. So okay, yeah, maybe we could dial that down a little bit. So GPU memory, we only used 2.7 gigs instead of the 4 I think we requested. And then physical RAM on the machine, again, we requested 4 and we ended up using less than half of that. So, there's room here for kind of reducing these resource requests. And maybe that means that we'd start matching more machines. These are already pretty modest requests already, so I'm not sure that we would get more throughput. So maybe it's better just to kind of leave that breathing room. So another thing that's possible that's way beyond the scope of this presentation is you can define automated workflows using something called DAGman. And so I linked the documentation here, but the idea here is you describe a graph of work that needs to get done using like parent-child relationships, and Condor will sort of submit jobs on your behalf as kind of the other nodes complete. And so this is conceptually what one of those might look like. This is kind of exactly what I just described. So maybe you're doing a hyperparameter sweep and you're changing your alpha parameter, your A parameter, and you're saying, okay, I want to try 0.01, 0.02, 0.03. And after each one of these trains to its full 30 epochs or 20 epochs, whatever I'm deciding in these experiments, I want to run the same evaluation for each of those models. Then I'm going to choose the best model out of that entire set that I ran, and then I'm going to do my inference on that. So you can define these workflows so that as soon as this one is done training, it will do evaluation, and as soon as this one is done training, we'll do an evaluation job. Then because all the parent-child relationships are defined, once all those evaluations are done, it can do the best model and then the inference kind of automatically. And so that's if you're doing this is how you start to do kind of true workflows, as you define these relationships and kind of have Condor do things on your behalf. And the final thing I want to say is think big, and you should really not be letting computing be a barrier for your scientific research. And so and we kept things pretty small here, but think about tens or hundreds of models. Think about tens of thousands of inference jobs. What is the science that could be really, really transformed by having access to a large amount of compute?
Yeah, our experience has been that folks who need to do like a lot of inference or a lot of even like feature extraction or things, data pre-processing, data post-processing, that's a really, really great fit for this high throughput computing approach because if you have 10,000 things or 10 million things, you can just submit that many jobs or group them together and get a lot of stuff running in parallel at once. So,
Yeah. And another one that I do want to mention is a lot of people are doing sort of really wide simulations, a bunch of simulation jobs on CPUs, and then using those simulations as input for a model training for, whatever their science needs. And so that's another fairly common, spread it really, really wide to do a bunch of simulations and then use that as your data set for the next steps. Great. Any
any
questions?
other questions?
Well, these are all the good things, but are there some cons for this?
Hmm. I don't know. Christina, you have.
Some what? Some goals?
No, no, cons. Like, okay, these are the
Oh,
good.
oh, oh, oh. I would
Yeah.
say the biggest one is data size. If you are
Yeah.
trying to train on a data set that's like 750 gigabytes, we are probably not the space for you just because, especially if you're only submitting one job and it's, your data is in New York and you're submitting from Chicago and your job is running in San Diego, like, um, moving that whole data set just to train a model is maybe not ideal. That said, we are working on, I feel like, some tooling or some features that would support something like I want to run a bunch of jobs, a bunch of training jobs, and how to bake reuse in so that, yes, you'd have to, the upfront cost of transferring the data set, but then you could train on it multiple times. So our prototype for this is actually experimenting with AlphaFold because it has about a 750 gigabyte um, database for the first step of the protein structure prediction process that doesn't use GPUs, to be clear. And what can we do to like stage it and then target where the data is staged so that you can run a lot of jobs using that staged data set. And then the second phase of AlphaFold doesn't have a large data set at all and uses GPUs and is really perfect HTC. So I would say that's the biggest thing is the actual like size of the data you need for a job. Um, and then the other limitation technically could be time because we're not going to let you run for like 3 days, but
Yes.
you shouldn't run for 3 days anyway. That's bad practice. So
Yeah.
we can help with things like checkpointing and machine learning is super resumable because it runs in epochs. So yeah, I would say data staging at like super large scales is really the challenge.
Yeah. Thanks, Christina. That gave me time to think of a couple more too. So, another is, it's another thing to learn. Like, learning how to interact with Condor is, just sometimes it's a hurdle. It's kind of an unfamiliar system. You're gonna have to figure out how to troubleshoot jobs. And then the other one we see quite a bit is, people are used to kind of having a Jupyter notebook on a GPU on a lab machine kind of thing. And it's the conceptual transition to kind of the batch mode of computing is a con as well in a lot of ways. So
Thank you.
yeah.
Yeah, I have a question. You were talking about using images, and what if I'm running a MATLAB code? I only need a MATLAB. Is there a way to do this? Thank you.
To do what?
MATLAB
MATLAB code.
code?
Yeah, yeah.
Oh,
Yes. Um, we've done it in the past. MATLAB is a little tricky because of the licensing.
Mhm.
So in the past, we've had two different approaches. One is MATLAB used to produce a compiler, their own custom compiler where you could like compile your MATLAB code into a binary, and then you could execute it without a license. So that was really great for distributed computing. And the runtime to run the compiled code was free. So you just needed the license to do the compilation, and then you could run it sort of as many times as you wanted without needing a license. Then one of my team members came up with a way to actually build a MATLAB container that can connect to a site license so that you don't even need to compile your code. You can just build this container and run it. So if that was something you were interested in, we would probably want to talk to see if that approach would work. It's a little nicer because then you can just have the readable MATLAB code. You don't have to do the compilation step. But there are avenues we can explore.
Okay. So either way, you need a container, right?
Yeah, you always need to bring along your software environment. Like
Okay.
the situation is a little bit like your friend is like, here's my laptop. Does it have everything installed you need?
Yeah, I guess that one. The other question is, I work with HPC. It's like something like you node some module, like standard module, like GCC, node GCC. Then we don't need a container.
Right. So that kind of setup has a hidden assumption that you have a shared file system or that all your nodes are exactly the same. And we'd have neither of those things on the OSPool. So that's why we really emphasize containerization and software portability.
Okay. Thank you.
Good questions.
Yeah, thanks for the questions, everyone. Any other questions before we wrap up?
Awesome.
Yeah, okay. Thanks, everyone.
Good.
Ian, your custom terminal setup is really sweet.
Thank you so much.
Mine's not that fancy.
Yeah. I've spent a lot of time on a terminal, so I've, over the last 15 years, I've built out something that makes me comfortable. Cool. Thanks.
Thank you
Thanks
so
for
much.
joining, everyone.
Yeah.
Thank you, guys.